Swayam Prabha. Digital India. Educated India.
Imagine a life-saving resource so vital that the entire health system depends on it. Yet, its delivery is riddled with inefficiencies, safety gaps, and uneven access. That resource is medical oxygen and its associated containment cylinders. In this project, on the oxygen cylinder ecosystem, its full supply chain from production and storage to regulation and emergency response was explored. What is revealed displays a complex web of stakeholders, manufacturers, frontline health workers, regulators, emergency services, and global standard bodies, all playing a role in delivering this critical gas. We have Rakesh, Arunima, Rashmita, and Abha with us, who will be taking us through an exciting project about intervening in the oxygen cylinder markets of India. We will dive into the world of oxygen cylinders, exploring their market trends, unique properties, and wide ranging applications. The team highlights the need for innovation, efficiency, and safety in how medical oxygen is handled and distributed. Whether for patients in ICUs, workers in hazardous industries, or communities struck by disaster, reliable and secure access to oxygen cylinders is not just a technical issue, it's a human one. Join us as we present insights, interventions, and a vision for a smarter, safer, and more inclusive oxygen supply system, one that's built to save lives, not just deliver a gas.
The healthcare oxygen cylinder market is vital to the health infrastructure because of life saving functions, increasing demand, and role in emergency planning. In our modules, we will consider numerous aspects of its production, distribution, and role in health systems.
To start this project, we first conducted thorough research on the medical oxygen supply chain, including production processes, storage and safety practices, regulatory environments, and market forces. We also investigated issues that occur during high demand situations, including health emergencies and located innovations that seek to enhance accessibility and efficiency. Throughout the project, we combined the analysis from industry experts, data studies, and case studies to give holistic picture of the medical oxygen cylinder ecosystem.
Our methodology is a systematic 5-step process to thinking through impactful interventions in the medical oxygen cylinder system. We start by framing the system wherein we define the limits of the medical oxygen supply chain, its critical stakeholders, and critical factors like production, storage, and distribution. We then proceed to comprehending the system, wherein we have an in-depth knowledge of how the system works, including regulatory norms, pattern of demand, and prevailing issues, particularly during healthcare emergencies.
From this, we move on to envisioning interventions, where we look at areas where we can strengthen the supply chain, enhance access, and enhance safety procedures. These concepts are then elaborated further in formulating the intervention, defining them as operational, scalable, and sustainable interventions. Also, we discuss enabling the transition, whereby our interventions are feasible to enact and integrate into the healthcare system so we can leave a lasting effect and sustainability.
In order to design in a complicated space, one must first limit the time and place of the system. This means that one identifies the important stakeholders, sets boundaries, and selects a topic by which the problem will be answered. In this task, we clarify the ways that we limited the time and place of the medical oxygen system to set distinct actors, environments, and interactions that define the system. Our attention extends to the producers, distributors, healthcare facilities, regulatory agencies, and emergency systems that are charged with offering timely availability and secure use of medical oxygen cylinders.
As we move to the broader context of the oxygen cylinder system, we are aware that it is managed by a web of varied stakeholders geographically, industry-wise, and sector-wise. The oxygen cylinder life cycle, production, consumption, and disposal stretches across a number of related players. To understand it from a holistic point of view, we can classify stakeholders as primary, secondary, and tertiary, and each of them plays a different role in maintaining this life-saving supply chain. Stakeholders at every level mutually influence one another. Their operational approaches and mindsets shapes overall system performance, and overarching policies guide and support these interactions.
Primary stakeholders are individuals and organizations directly engaged in the production, handling, transportation, and frontline use of oxygen cylinders. Foremost among them are the end users, from patients in hospitals and at home to industrial workers utilizing oxygen for welding, cutting, and chemical reactions. Medical personnel, firefighters, scuba divers, astronauts, miners, and soldiers all depend on oxygen cylinders for protection and survival in adverse environments.
Industrial producers consume oxygen in huge amounts to produce steel, process petrochemicals, and make glass. Construction workers, shipbuilders, and metal fabricators often conduct welding and metal cutting processes in oxygen cylinders.
Cylinder manufacturers, filling stations, and distributors have the responsibility for safe production, filling, and distribution of oxygen cylinders. Organizations for testing and inspection provide assurances of safety levels, while maintenance contractors perform periodic maintenance, hydro testing, and valve replacement.
Secondary stakeholders. These organizations might not be directly involved in the case of oxygen cylinders, but plays a significant role in facilitating, empowering, or enhancing their use across industries. These include gas manufacturers, equipment suppliers, and valve and regulator manufacturers who assist in designing safer, lighter, and more effective cylinders.
Training centers, vocational schools, and certifying agencies offer needed education and standardization for operators of oxygen cylinders. Workplace safety instructors, industrial health officers, and emergency readiness personnel are all significant elements of risk reduction.
Tertiary stakeholders are institutions with indirect but system wide impact, ranging from policy making and funding to advocacy and public outreach. Government ministries, for example, industry, health, and environment ministries, establish standards in terms of cylinder manufacture, gas quality, emissions, and worker safety. International standards institutions like ISO offer safety and material standards.
Lastly, NGOs, disaster relief agencies, and humanitarian organizations provide disaster oxygen access, and research communities and scientific organizations continue to evolve materials, increase safety, and work on sustainable substitutes.
Before we proceed to discuss the medical oxygen cylinder life cycle, let us first clarify the stakeholder dimensions. This will enable us to better comprehend the manner in which various players involve against the system and how the quality and quantity of oxygen delivery may vary based on the players.
At the core, we're looking at several key factors that shape the system. Let us begin with oxygen concentration. In lower level sources, the oxygen levels go below 80%, which is dangerously inefficient, especially in emergencies in the medical field. Yet, prescribed High purity sources yield up to 99.9% pure liquid oxygen, which is the medical gold standard.
Next, consider distribution methods. Low-end machines are constructed around small bedside cylinders, simple to install but of low capacity. High-quality systems employ central manifold piping that supplies entire hospital floors with a smooth flow.
Then there is a cylinder capacity and size. At the lower end, cylinders with around 85 to 100 liters water capacity exist. Industrial or high-use medical environments with cylinders of up to 1 lakh liters and 80 into 12 inches dimensions and weighing around 200 kilograms.
Now, let us discuss portability and pressure requirements. These must be smaller, lighter cylinders to use with home patients or in small industrial uses. Conversely, heavy duty, high pressure cylinders are used by medical professionals, emergency responders, divers, and people who work in dangerous environments.
Then there's accessibility. Sadly, in open markets, access can be unsafe, with cylinders not necessarily being up to safety standards. While in controlled environment, there is adherence to FDA, WHO, ISO, and local rules for the safest product.
And lastly, regulatory compliance. Black market distributors tend to circumvent important safety standards, and this contributes to elevated risk during crisis. Conversely, the compliant suppliers follow rigorous standards for protecting both handlers and users.
To summarize, the medical oxygen cylinder system is influenced by several factors such as oxygen purity, distribution methods, and regulations. High purity oxygen, that is up to 99.9%, is essential for medical use, unlike low grade sources that fall below 80%. Distribution varies from small bedside units to centralized hospital systems. Cylinder sizes and pressures differ by use, with portable models for home and large high pressured ones for industrial or emergency settings. In regulated environments, safety standards ensure proper handling, while black market access poses serious risks due to non compliance. Therefore, when we think about oxygen, we should not be simply thinking about a specific product in a cylinder. We are thinking about a range of products in a cylinder requiring several processes of manufacture and refinement.
So, an oxygen cylinder is a very important product that needs further comprehension and needs to be addressed from a systemic viewpoint. For starters, it is a pressure vessel to carry and store oxygen for medical, industrial, and aviation use. Constructed of robust materials such as steel or aluminum, it is available in sizes from portable to large stationary tanks.
Now let me tell you about the production process of oxygen filled in cylinders first. You have to know it, particularly for medical emergencies like the COVID-19 pandemic situation, where supply of oxygen turned into a life and death matter. Oxygen filled in cylinders is manufactured through methods such as cryogenic distillation or pressure swing adsorption.
In oxygen plants, atmospheric air undergoes a multi-step process to extract pure oxygen. First, the air is compressed, filtered to remove dust and pollutants, and then chilled. Impurities like hydrocarbons are burnt off. The remaining oxygen nitrogen mixture is cooled to around minus 165 degrees Celsius, causing oxygen to liquefy. This liquefied oxygen is then stored in cryogenic tanks, which maintain extremely low temperatures to prevent evaporation. From these tanks, the oxygen is either filled into cylinders or transported in insulated tankers for medical and industrial use. This process ensures high purity oxygen critical for healthcare, especially in emergencies and intensive care.
Then there is the oxygen cylinder itself. Cylinders are constructed from different materials like steel, aluminum, and composites and are graded into types type 1, type 2, type 3, depending on their construction and material composition. The oxygen is stored under pressure in the form of gaseous or liquid state inside these cylinders. Cylinders are color coded for identification. Medical oxygen cylinders, for example, have a white shoulder and a black body.
Where there is transportation involved, the medium is a function of the distance. For distances under 200 kilometers, cylinders are used the most. For 200 to 500 kilometers, mini bullets in an insulating jacket do best. For over 500 kilometers, cryogenic tankers are used most since they can sustain liquid oxygen on a long distance haul. Now let's discuss the problems. Supply chain problems, human resources shortage, infrastructure shortage, and finance can threaten oxygen cylinder access. Moreover, during crisis, these challenges often get magnified.
Cylinder safety is a major concern due to the high pressure and flammable nature of oxygen. Overfilling, rough handling, and neglecting timely maintenance can lead to explosions or gas leaks. Faulty valves, worn out regulators, or rust buildup inside cylinder compromise structural integrity. Even minor leaks can create oxygen-rich environments, significantly increasing fire hazards. Therefore, regular inspection, proper training, and strict adherence to handling protocols are crucial, ensuring that cylinders are stored upright in ventilated areas and away from heat sources. Further reduces the risk, making safety a top priority in both storage and usage of medical oxygen.
The entire life cycle of medical oxygen cylinders range from gas manufacture and cylinder fabrication to distribution, use, and safety measures. This involves important stages such as raw material extraction, cylinder production, testing and inspection, oxygen production, cylinder filling, storage and distribution, end use, refilling and maintenance, and end of life management. Let's discuss this a little bit further.
The initial process is the obtaining of the raw materials used in the production of oxygen cylinders. These materials can be steel of high quality, aluminium, or composite such as carbon fiber. The material is mined, processed, and then purified to standards that can ensure safety and necessary strength in containing high pressure gases such as oxygen.
After the materials are fabricated, they are then formed into cylinders. Cylinder fabrication is the process where the metal or composite material is formed into a hollow pipe, and then comes the creation of the neck, a vital stage, as this is where the regulators and valves will be mounted. For composite cylinders, this is where the fiber and resin layering occurs. After they have been formed, the cylinders are heat treated for hardening, then surface treated by sandblasting, coating, and painting to prevent corrosion and impart durability.
All these cylinders undergo intensive testing and inspection before they are certified for use. The tests involve hydrostatic pressure testing to confirm whether they can withstand high pressure levels, ultrasonic testing to confirm whether the structural integrity of the cylinders is satisfactory, and visual examination to confirm detection of any faults. Safety here is important since the cylinders will subsequently contain life-sustaining oxygen under high pressure.
After testing and cleaning, the cylinders are fit for filling. The oxygen is compressed and stored in the cylinders at extremely high pressures, often between 150 to 200 bar. The cylinders are sealed, installed with the necessary valves, and marked with information necessary, such as the purity level, inspection date, and procedure for handling upon filling.
Filled cylinders are properly stored in dedicated areas, free from heat or inflammable materials. They are delivered safely to home care services, ambulances, hospitals, or clinics through specialized logistic networks. It is crucial to keep the integrity of cylinders undisturbed during transit to ensure safety.
Once used, spent cylinders are returned for examination and refilling. They are cleaned and checked for wear or damage before they are refilled. Maintenance costs of valve replacement, leak check, repainting, and pressure test to be safe for use again.
Cylinders that have come to the end of their life are decommissioned responsibly. Steel and aluminium cylinders are recycled, while composite cylinders are broken down and processed in line with environmental standards. There is also increased focus on green practices, waste reduction, and promotion of eco friendly recycling.
Let us proceed to the learning of the system now. We start with the understanding of the use of oxygen cylinders in various industries. Oxygen cylinders are employed in all sorts of environments, from daily healthcare requirements to hostile environments. Whether it is sustaining human life, improving performance, or supporting industrial processes, oxygen is a part of numerous systems surrounding us.
Medical oxygen cylinders are an integral part of the health system, being a life saving product in intensive care units, operation theaters, ambulances, and even in home care in chronic respiratory patients. In times of health emergencies, such as the COVID-19 pandemic, their role intensified as they were used as a frontline measure in the management of severe respiratory diseases.
In manufacturing, oxygen is significantly utilized in cutting and welding processes, particularly with metals such as steel and aluminium. Glass production, paper production, and even food processing firms also use oxygen for uses such as combustion, efficiency, sterilization, and packaging.
Another significant industry is aviation. Oxygen systems are installed in aircrafts at high altitudes to assist pilots and crew during the time when atmospheric oxygen levels drop. In diving and submergence operations, oxygen cylinders are designed for scuba diving, rescue, and underwater construction work, allowing divers to breathe comfortably and safely in deep water.
Out of all the oxygen delivery systems, we selected medical oxygen cylinders as our point of research due to their extensive use, portability, and importance in emergency situations. Their application towards improving access to healthcare, especially among rural and underprivileged areas, make them the front runner in medical preparedness and fortifying our healthcare systems against upcoming challenges.
Medical oxygen cylinders are strong aluminum or steel and high pressure resistant. They are available in all sizes, from portable equipment to enormous hospital cylinders, and have valves and regulators for the safe dispensing of oxygen. Oxygen itself is odorless, colorless, and tasteless, but cylinders are color coded. They are usually green or white in color. They are so designed that they can be safely manipulated even under harsh conditions.
Medical cylinders hold approximately 99.5% pure oxygen, an essential compound for cellular metabolism and energy production. Although oxygen is not combustible, it aids burning violently and therefore safe storage is essential. Healthcare oxygen is also employed in sterilization, enabling infection control.
Medical oxygen cylinders are primarily of steel, aluminum, or carbon composites. Steel is heavy and strong, aluminum is lighter and easier to ship, and carbon composites are the newest, light, tough, and capable of withstanding high pressure. But manufacturing has real challenges: shortages of materials, increasing production costs, and constant pressure to maintain strict safety standards. The silver lining: technologies such as lightweight composite cylinders are causing efficiency to increase. They reduce the cost of transport, are simpler to control, and inflict less harm on the planet. Typically, this phase comes with its own problem, but it's also where intelligent materials and design decisions are making oxygen cylinders cleaner, cheaper, and safer.
Now, let's talk about supply and transportation. This is the most critical phase because no matter how well cylinders are made, if they don't reach those who need them, they're useless. Issues here are city and rural supply deficits. The cities have priority access, with remote areas being left behind. Not even real time tracking is being done, leading to delays and even cylinder hoarding, primarily during emergencies. Black market prices skyrocket during crisis, and it becomes even more difficult to obtain. What we require is improved logistics, intelligent tracking systems, and cleaner channels of distribution. This would provide timely delivery, curb abuse, and make the whole supply chain stronger.
Next, let's talk about handling and uses, a stage where safety becomes absolutely critical. Medical oxygen is life saving, but it's also hazardous if not handled properly. We are talking about risks like leaks, fire hazards, and improper storage. For example, cylinders must always be kept upright and far away from flammable substances. Unfortunately, not everyone is trained well, which increases this risk. Needed is improved safety instruction, clearly set rules, and frequent inspection to ensure use is as safe as can be.
Lastly, there is recycling, too frequently forgotten but an indispensable step. Most of the oxygen cylinders are reusable and recyclable but are dumped since recycling them is too expensive and there is no incentive. This is an environmental and economic missed opportunity. We must follow circular economic practices where cylinders are recycled occasionally and components reused. It would make the system more effective, sustainable, and less prone to disruption, particularly during peak demand.
In other words, we need to comprehend the issues in a much broader light due to the focus on the overarching system. As we had mentioned in the first lecture, the iceberg is an important metaphor to depict systems. This metaphor allows us to identify surface level problems as well as deeper level problems that are often hidden but lurk in the depths. In the case of the iceberg model, there are hidden layers of challenges, such as in the medical oxygen ecosystem. On the surface, issues like transportation delays, equipment failures, rural shortages, and inadequate training are visible. Deeper, systemic level problems include fragmented supply chains, weak regulations, and poor environmental management. At the level of worldview and values, there is a tendency to prioritize cost savings over safety and a lack of investment in robust systems. At the deepest level, a belief persists that failures in the system are inevitable, reducing motivation for innovation and reform.
Now, let's dig deeper with the iceberg model to see the hidden levels of the medical oxygen cylinder system. At the litany level, we observe obvious issues like transportation delays, equipment failure, rural shortages, and inadequate training. These issues have significant safety risks and inefficiencies.
At the structures and systems level, it becomes more complicated. Supply chains are fragmented, regulations sometimes are weak, and environmental risks through mismanagement persist. These systemic deficiencies worsen accessibility and increase dependability.
At the worldview and values level, we find deeper assumptions. There's a lean towards saving at the expense of safety. There's no investment in solid systems. And complacency keeps such inefficiencies on their feet.
Lastly, at a deep myth level, there is a belief that oxygen cylinders are rescuers and can also turn into dangers. Failures are seen to be unavoidable, lowering the necessity to innovate and enhance the system. In order to achieve the real change, we need to address each level of this model.
From the gigamap that was developed, there was a deep dive into the medical oxygen cylinder system and a zip analysis was conducted. This zip analysis allowed for the identification of focal points of intervention, areas that have larger issues and potential for improvement.
Through close observation, we found 5 significant intervention points within the system. First, let us discuss the material used in medical oxygen cylinders. Most medical oxygen cylinders are of steel, aluminum, or composite carbon materials. But look, there lies a problem: shortage of materials, costly manufacturing, and necessity of rigorous safety codes. Light composite cylinders, for example, are an exciting development. They are lighter, less bulky, and safer. But the problem remains one of the scaling them large enough. Here there is a room to find other more green material or even modular construction that could solve manufacturing limits.
Second, transit delays. During crisis, we have seen how delays in oxygen transport have cost precious lives. Lack of real time tracking, inefficient logistics, and dependence on overburdened routes severely affects timely delivery. Urban areas might still manage, but rural areas suffer the most. These technologies, like smart logistics, GPS tracking cylinders, and decentralized storage facilities, may well meet this need, but implementing them at a scale is a major operational challenge. Third, the undersupply of oxygen in rural regions. This is a persistent issue. Most rural health units are reliant on unpredictable cylinder supplies and the occasional black markets in times of crisis. Shortages in supply chains, poor awareness, and infrastructural shortcomings all add to the issue. Possible interventions include mobile oxygen cylinder plants, local filling stations, or community based cylinder banks. Affordability and maintenance, however, are still a concern.
Fourth is equipment malfunctions. Cylinder leaks, defective regulators, damaged valves. These are not uncommon events. Inadequate maintenance procedures and low quality equipment increase the risk, particularly in working class clinics and hospitals. Enhanced maintenance training, periodic audits, and quality assurance by certified manufacturers will greatly mitigate this risk. Pressure sensing smart cylinders also have scope to offer early warning for malfunction. Lastly, inefficiencies in oxygen cylinder handling and improper training. This turned into a very serious situation. Leaks, risk of fire, and explosion are the results of improper handling. Most of the frontline employees and emergency personnel receive no training in the safe handling of cylinders whatsoever. E.g., straightforward methods and practical training courses would be a significant distinction here. Producing easy to produce digital tutorials and visualized safety guides would raise the safety and productivity level instantly.
Although all 5 interventions are valuable, enhancing inefficiency in handling and inadequate training were found to be the most viable, high impact point of leverage. Why? Because it is simple to roll out, low cost, and can potentially hugely cut accidents and wastage. By giving the right information and tools to the people, we can make the system safer, stronger, and a lot more efficient without having to wait for large infrastructure changes. And that's how we came up with our leverage point.
Up till now, in our system analysis, we observed several intervention points across the oxygen cylinder supply chain, from manufacturing to end use. However, safety and efficiency in usage and handling emerged as the most critical leverage point. These factors directly impact human lives, operational continuity, and the prevention of accidents or wastage. Focusing on improving training, implementing stricter safety protocols, and adopting better technologies at this point can create significant positive ripple effects throughout the entire ecosystem, ensuring reliable supply, protecting healthcare workers, and reducing overall system risk and cost.
That is because inefficiencies in the use and handling of oxygen cylinders don't just slow down operations. They endanger lives, escalate cost. Improper storage, rough handling, or ignoring maintenance can lead to dangerous leaks, fires, or even deadly explosions. These incidents not only result in human loss but also damage infrastructure, disrupt healthcare delivery, and create a cascading effect of financial strain, legal liabilities, and public distrust. Moreover, wastage of oxygen due to leaks or mishandling during emergencies can mean the difference between life and death, especially in critical care settings. Ensuring proper training and safety protocol is non negotiable.
Let's break that down a bit. A few of the most frequent safety concerns are mis-storage, where cylinders topple over, leak, or even explode. Fire risks, where cylinders are carried too close to fire or sparks. Incorrect uses like overpressurization or misuse of valves and regulators. All of them can be avoided if the people who are working with oxygen cylinders are properly trained. Now comes the critical question: how do we fix this?
We tried a variety of solutions, such as stricter regulations, installing more sophisticated monitoring equipment, or replacing the equipment. They function, but they are treating symptoms, not the underlying systemic issues.
The real issue lies in mishandling due to poor training. Current training methods fall short. Let's be honest. Manuals are ignored or quickly forgotten. Passive video tutorials don't prepare workers for real emergencies. One time lectures lose their impact over time.
What workers actually need is not more information, but practical experience. They need training that's interactive, memorable, and replicates real world situation they will face on the job.
Yeah, that's exactly where our solution comes in: OxyQuest. OxyQuest is not just another training program, it's not just another item on the checklist or a standard presentation that workers sit through passively. OxyQuest is something more. It's a gamified, interactive learning tool thoughtfully designed to teach oxygen cylinder safety through engaging scenario based decision making by immersing users in real life simulations. It replaces monotony with motivation and replaces passive observations with active participation. Learners face time sensitive choices, collaborate with peers, and respond to emergency situations in safe environment, building skills, confidence, and muscle memory that translate directly to real world preparedness and accountability.
Instead of reading about hazards, instead of listening to someone talk about what might happen, workers actually experience realistic challenges, the kind they already encounter in their day to day operations. And they experience it in a safe, structured, and immersive way. That's the real power of OxyQuest. It doesn't just teach, it simulates. It creates learning through doing.
Now let's break down the core content of the game. OxyQuest covers three safety zones, each focused on different stages of oxygen cylinder handling. The first zone is storage. Here the game teaches best practices for proper safe cylinder storage. Players learn where to store cylinders, how to segregate full from empty, how to prevent tipping, and what temperature conditions are considered unsafe. These aren't just abstract ideas, they are turned into challenges. If a player stores a cylinder incorrectly, there's an in game penalty. If they do it right, they get rewarded.
The second zone is transportation. This part of the game simulates the safe movement and secure delivery of cylinders. We all know how much can go wrong during transport, like loose trolleys, unsecured cylinders in vehicles, walls getting damaged. In OxyQuest, these scenarios play out visually and interactively. The player has to decide, how do I move this safely? What's the right equipment? Is the van properly ventilated?
And finally, we have maintenance and emergency response. This zone is not about routine. It's about those moments when something goes wrong: a fire, a leak, a equipment failure. In this part of OxyQuest, workers are trained to respond effectively and calmly. They are presented with situations like: there is a hissing sound near a valve. What do you do? A small fire breaks out near a storage room. What's your first move? By cycling through these zones, workers gain a full circle understanding from proper storage to safe movements to emergency management. But more importantly, they build situational awareness.
Now let's talk about the gameplay itself. OxyQuest is structured to run in rounds, and each round represents a realistic scenario based challenge. Each round begins with a scenario card. This card presents a workplace situation drawn directly from real life incidents, safety case studies, or even reported near misses. These aren't made up or hypothetical. They are things that have happened or could easily happen in oxygen cylinder handling environments. For example, a worker might be asked, "You have been asked to move 5 oxygen cylinders across a bumpy warehouse floor using a standard trolley. What's the safest way to do this?"
Players must assess the risk in each situation, choose an action, and explain their reasoning. If they make the right call, they earn tokens. If the decision is wrong or risky, they get penalized. These rewards and penalties aren't just for show, they are designed to mirror real life consequences. A careless decision about how to transport a cylinder could result in damage, fines, or even injury in the real world. In the game, it translates into losing points or missing opportunities to progress. So the feedback loop is immediate and memorable.
And here's what makes it even better: it's not a solo game. Players learn from each other. They'll talk, observe, challenge each other's thinking. If one player makes a mistake, the others can discuss it. If someone handles a scenario brilliantly, that learning spreads instantly across the table. It's peer learning. Without forcing it, it happens organically within the game mechanics.
Can a single game format serve everyone? What if some workers are experienced and others are new? Yes, OxyQuest is designed to be inclusive. It includes hints and teamwork opportunities so players with less experience don't feel left out. It encourages groups to work together, to pool their knowledge, and to strategize. It also includes a strong observation component. Watching someone else make a poor decision and understanding why it was wrong is often most powerful than being told the right answer.
You might wonder, how is this better than a full scale safety simulation? Well, simulations are great, but they're also costly, often hard to repeat, and limited in reach. In contrast, OxyQuest is affordable. The physical components or digital versions are easy to replicate. It is reusable. Every session is different because of the varied scenarios and outcomes. It is also scalable. It's ready to be used in hospitals, factories, warehouses, and transport hubs, anywhere oxygen cylinders are handled. And this is the key: it's portable and simple to implement. You don't need a high tech setup, you need a table and a group of workers.
OxyQuest isn't just a game, it's a transformational approach to workforce safety and preparedness. By making learning interactive and practical, we empower workers to handle oxygen cylinders safely and confidently, reducing accidents, improving efficiency, and ultimately saving lives. This is how we turn our leverage point into a real scalable solution.
So far, we have identified critical failures in oxygen cylinder handling and developed a practical, engaging solution, that is OxyQuest. But to transform this from an exciting innovation into a revolutionary transformation, we need to move beyond design.
Our first priority is to redirect the oxygen supply chain to contemporary standards of safety and to develop worker capacity at scale. OxyQuest equips frontline workers with knowledge as well as with confidence to make transparent decisions in times of need. Through interactive, scenario based gamified learning, we substitute passive memorization with active experiential immersion so that safety protocols become second nature.
OxyQuest is not meant to be a one and done event. For OxyQuest to create a real impact, it needs to become a systematic part of a safety ecosystem. First, we propose embedding OxyQuest directly into standard operating procedures. That means every worker interacts with this tool as part of regular safety routines, not just during special workshops.
Secondly, we introduce mandatory training cycles. Like safety drills, OxyQuest can be replayed every quarter or every 6 months. This keeps knowledge fresh and sharp. Even experienced staff benefit from revisiting the scenarios. Third, OxyQuest becomes part of onboarding. For new recruits, it's their first hands on experience with safety. Instead of flipping through a manual, they're playing, deciding, and learning and retaining it.
And fourth, we align OxyQuest with regulatory frameworks. It mirrors hospital and WHO safety guidelines, which means it's not just educational, it's compliant. Compliance becomes memorable, not just mandatory. OxyQuest effectively transforms compliance from a routine checklist into an engaging, hands on learning experience. It mirrors hospital safety protocols and aligns with WHO guidelines, presenting users with real world scenarios that require the direct application of these standards. As users navigate through gamified challenges and receive immediate feedback, the compliance requirements become intuitive and memorable. This immersive approach not only reinforces the importance of following safety guidelines, but also may lead to higher adherence and better operational safety outcomes in practice.
Now, let's talk about how OxyQuest works across different contexts. Safety needs may vary, right? What workers in a large hospital might need tweaking for a small industrial plant. That's why we have ensured OxyQuest is customizable. Trainers can adapt game cards and scenarios to reflect local risks and regulations. Multilingual, all materials can be translated and localized, so language is never a barrier. Digitally accessible, a mobile-friendly version allows worker to play on the go or as a part of hybrid training. Train the trainer ready. We have developed modules to equip facilitators so the implementation is consistent and scalable across different units and geographies.
But that is not sufficient integration. OxyQuest seeks to create a culture of safety ownership such that all employees become engaged stakeholders in protecting their world. Critical thinking. Employees don't just memorize procedures, they are trained to access situation and make smart decisions in the moment. Second, collaborative learning. Interactive decisions about game situations leads to cooperation and shared accountability. Third, gamification for motivation. Friendly competition makes learning a stimulating, fun experience, fueling engagement and retention.
OxyQuest is more than a course of training. It's an interactive, game based learning solution designed to immerse students in the principles of oxygen cylinder safety. Rather than passive lectures or one time workshops, OxyQuest places learners in real world scenarios that mirror the everyday challenges. Through decision making gameplay, it fosters critical thinking, teamwork, and a deeper understanding of the consequences tied to their actions, creating a more impactful and lasting educational experience.
Our next steps are clear and actionable. Pilot programs. We will launch OxyQuest in varied training environments to test its adaptability and measure its impact on learning outcomes. Having iterative refinement. Feedback from real sessions will help us fine tune scenarios, improve game dynamics, and enhance realism. It can also scale and expand from hospitals to transport hubs, from emergency services to factories. We are ready to roll OxyQuest out wherever it's needed.
With OxyQuest, we are not improving the way workers get educated about the safety of oxygen cylinders. We are rewriting the training playbook at work from scratch. By enabling safety training as an immersive experience, a ready access solution, and an integrated engagement, we moved closer to a day when every oxygen cylinder is handled professionally, carefully, and confidently.
By integrating OxyQuest into training initiatives, we enhance not just safety protocols but the very fabric of oxygen cylinder handling culture. It is not a game, it's a catalyst for sustained behavioral change. With scalable design, accessibility, and participation, OxyQuest equips workers to become alert, assured, and proactive guardians of safety. Collectively, We make a leap towards safer workplace, reduced accidents, and a future where every oxygen cylinder is treated with care and respect.
The project provides a comprehensive overview of the medical oxygen cylinder system, emphasizing its critical role in healthcare, particularly during emergencies like the COVID 19 pandemic. It explored the full life cycle of oxygen cylinders from raw material extraction and production to distribution, usage, and recycling. Key challenges identified include material shortages, unsafe handling, rural supply deficits, equipment failures, and poor training practices. Training was identified as a key intervention point to improve safety of oxygen cylinder handling. The team developed OxyQuest, a game-based interactive training tool designed to improve safety in cylinder handling through engaged scenario-based learning. By targeting common safety risks and empowering workers with experiential training, OxyQuest aims to reduce accidents, increase efficiency, and build a culture of accountability and preparedness. The project demonstrates how the world of oxygen cylinders can be addressed systemically and systematically to enable alternatives. The ultimate goal is to make oxygen delivery safer, more accessible, and resilient, especially in underserved and high demand settings.
When Copernicus said the earth revolves round the sun, it was considered blasphemy. When Galileo said the earth was round, we thought he was mad. When Darwin said that monkeys are the ancestors of man, we thought he had lost it. When the ecologists said this was the end of the world and the human race, we didn't believe them.
Hello, good morning everybody. I am Raghunandan Sengupta. So, I will just give you a very brief excitement area of finance, which is quantitative finance, and that has a huge market starting around about 10 years back, and it is exploding exponentially. So, what do we mean by quantitative finance? Quantitative finance is actually the application of different mathematical and statistical techniques in the area of financial markets, be it say for example derivative pricing, be it in the area of say for example portfolio management, be it in the area of asset liability management, be it in the area of portfolio management. We see that the application has exploded in such a way that there is a huge opportunity for people who have a quantitative background in mathematics and statistics. They can utilize those in the area of finance, but obviously with some prior knowledge of finance as a subject. Now, when we say about quantitative finance, as I said, it is an area of applied mathematics and statistics applied in financial markets. Use of different areas, if somebody is interested to know, we have stochastic calculus, we have derivative pricing, we have operation research, we have quantitative techniques like differential equations, stochastic calculus, time series, and they are heavily used in the area of quantitative finance as I mentioned. Now, we all know that in 1997 the Nobel Prize in economics, so it is basically the Nobel Memorial Prize in economics was given to the work of Merton and Scholz in the area of derivative pricing, and after that there has been an exponential increase in the area of quantitative techniques in quantitative finance and in the area of different type of derivative pricing. With the advent, moreover with the advent of high-ended and sophisticated computing data, big data has come in a very big way, where application areas starting from computing, from different type of algorithm design have been taken up in such a big way that nowadays at least we are able to understand that how high frequency data algorithm trading can be utilized using the concept of quantitative finance in the area of finance as such. But there is a flip side also, obviously when there is a huge amount of development. So, obviously due to some regulation errors or something, there has been some pitfalls, which I think is should be a bullet point for people who are really interested to take up quantitative finance, they should be aware. So, consider the financial crisis in 2008 and later on, and we are seeing different banks are failing, different financial institutions are facing a problem, countries are facing a problem like in Europe, in USA. So, what should be done? So, the main thing is that even if you know the technique is best for people who are investors, who are private players, organizations like banks, governments should use these techniques in a very somber manner, such that the application areas of quantitative finance using the techniques which we learned can be utilized in the best possible way to garner the overall the in depth knowledge a person has in trying to utilize these quantitative techniques in finance. And I am sure that people who have the background, who have the knowledge, who have the sophistication, who have the knowledge of the society can definitely use quantitative finance in a very big way in trying to make their mark in this exciting field, which you are going to see in years to come. And I am sure it will be a very exciting learning tool for all the participants who will take quantitative finance as a subject in years to come. Thank you, and I wish all the participants all the best and best of luck for the programs they will take. Thank you.
Hi, my name is Gillette Sam, and I teach sociology at IIT Kanpur. Today, I want to tell you a little bit about what sociology is. In order to go ahead and study sociology, one of the things you need to develop is a sociological way of thinking. Now, this capacity to think in a sociological manner was termed as the sociological imagination by an American sociologist called C. Wright Mills in 1959. He argued that in order to think in a sociological manner, you should be able to have two different skill sets. The first skill set would require you to have the capacity to think beyond the problems that individuals face. So, if you encounter a problem that some one individual is facing, you should be able to connect it to a broader public problem. Mills gave the example of people in his neighborhood. He says if there is one person who is unemployed in the neighborhood, that seems to be an individual problem. But as a sociologist, you're expected to dig around a little. So you come across a couple of other people in your neighborhood who are also unemployed. That indicates to you that rather than being a specific problem, there is a larger public issue at hand. So as a sociologist, you're supposed to look at individual problems and see how they are connected to broader public issues. The second capacity that you're expected to develop as a sociologist is the capacity to link an individual's biography with history. Historical thought may not come to you as the first thing that's connected to sociology, but it plays a pretty important role in the field. So Mills argues that rather than looking at a problem in the here and now, it's important to trace that long historical trajectory that may be connected to this individual problem. Let me give you an example from India, right? Let's say you look at the women in your family. Let's see at what age do they get married. So you may see that your sibling is getting married at the age of 25. Go back one generation. At what age did your mother get married? You may find that she got married a little younger, let's say 21. Go back another generation. At what age did your grandmother get married? You may find that she got married even younger, 18 or possibly even younger than that. So this capacity to see how the history of a family then influences the age at which your sibling got married, that is the capacity to bridge the biography of a person, or rather by a biography we can also think of the biography of a particular problem with history. What has happened in the past? How is that connected to this individual or this problem in the present? Thank you.